Hello everyone, welcome back to the YouTube channel. So, first of all, I would like to congratulate those of you who just got your AS level result or A2 level results. So, congratulations, I hope you're happy with that. And those who finish A levels, all the best for your future endeavors. But anyways, we're going to keep doing questions, we're going to keep going. So, today we are looking at question 4. Specifically 4D from February-March 2025, question 4, paper 42. So this is a very, very recent paper actually. Yeah. So without further ado, let's get to it. 4D. The crystal generates ultrasound waves that are used to obtain diagnostic information about internal structures. Roman 1. The crystal is made from piezoelectric material. Okay. I'm not sure if it's piezo or piezo. I think it's piezo. Piezoelectric material. But I got so used to pronouncing as piezo. So if I ever pronounce piezo while I'm explaining, please forgive me. Okay, because what matters is you understand. The listening part, pronunciation doesn't matter, because it's physics. Right? Okay, anyways. Explain how the crystal is made to vibrate. This is a 2 marks question. Okay. So before we start answering the question, I would like to talk a little bit about this piezoelectric thing. So I'm going to just write PZE because it's too long. So piezoelectric effect is something that is used to detect ultrasound or generate ultrasound. So where do you experience piezoelectric effect? So there's something called piezoelectric transducer. So if you've not seen a transducer before, this is how a piezoelectric transducer looks like. So usually this ultrasound application is very famous for pregnant mothers. They use this transducer with some gel and then they just move around the stomach to see how the baby is. And this is not only for pregnant mothers, it can work for any part of your body as long as the tissue reflects and you can read the image from the ultrasound machine. So this is how your transducer looks like, and if you can see there's a piezo element here. This piezo element is actually called as piezo crystal, and this crystal is called as quartz. So in A-level syllabus, this quartz is made up of lattice structure of silicon dioxide. Yeah, and surrounding this quartz there is something called electrodes. So this is the part where we're going to see how the piezoelectric effect works. So just extra knowledge, if let's say, Cambridge were to ask you, sometime at end of every question, not every question, but certain question, they'll ask you to suggest something. So if Cambridge were, to ask you to suggest other materials that can use to replace silicon dioxide that can be used as piezo element, what would it be? So there is something called PZT crystal. It's not in A-level syllabus, like I said, but it's good to know. And this is how your PZT material looks like. So why is it called PZT? Because P stands for lead, T stands for titanium, Z stands for zirconium. So PZT material. But there's also some oxygen, as you can see from this structure. But of course, it's not part of a syllabus, but it's good to know, because sometimes you never know, who knows, they might ask you to suggest something. Then, you have an answer and you get a free 1 mark, right? So, yeah. This one's for you. Okay, now let's go back. So, we talk about the... Okay, PZE transducer. And inside the PZE transducer, there's something called PZE crystal. And that crystal is made of quartz, and the quartz is made up of a lattice structure of silicon dioxide. So this is how silicon dioxide looks like if you're not familiar with it. But if you take chemistry, I think you'll be very, very familiar with this structure. Silicon dioxide. So we have silicon and 4 oxygens. Usually it's written as SiO2. Sometimes it's written as SiO4 because silicon can also be drawn this way. But now we are looking at SiO4 structure. Yep. but we still call it silicon dioxide. But this is in tetrahedral, which is not really necessary in this part, I'm just telling you. So now we are going to look at how this piezoelectric effect in the quartz works. Okay. Oh, also another one thing I forgot to mention. Transducer. So the word transducer actually has a meaning. So transducer is something that converts energy from one form to another. So in this case, you can convert mechanical energy to electrical energy or vice versa. So example of mechanical energy would be like sound wave, in this case we're looking at ultrasound. So of course, piezoelectric crystal is not only available in piezoelectric transducer, it's also available in microphones as well, where it converts mechanical energy to electrical energy, sound waves to electrical energy. And of course, example of electrical energy would be electricity. So another tip for you, if they ask what are other applications that you can use PZ crystal, microphones can be one of it. And also a lighter, burner lighter, that is another one of it. Okay, so now let's get back to our piezoelectric effect in quartz. Okay, so now I'm going to draw the transducer here. I know it's not that nice, but you get the idea. Okay, so this is the quartz, blue color, and it was surrounded by electrodes. So if we take a slice of this quartz, this is how it would look like. So if I were to draw it nicely, it looks something like this. Something like this. But is this the only way the structure can look like? No, it can also look like this. Of course, it can look like this as well. It depends on how you rotate your structure and how you cut the structure. So this is just one of the examples, but both is the same structure. Okay, now let's look. So let's look at this first diagram. This first diagram shows that they say that there's no stress. That means imagine now the transducer is not receiving any sound, any ultrasound wave. So there's nothing inside. So this is how the crystal would look like. Okay. And if you realize, here they have labeled positive, positive, positive. So this is showing that the silicon is positively charged and oxygen is negatively charged. Okay, now we're going to look at the center of charge of this molecule. Okay, let's first see the center of positive charge. Okay, let's use this orange color. Center of positive charge. So how do I find the center of positive charge? It's actually by drawing a triangle. Okay, this doesn't look like a very nice triangle. Let me draw it again. Okay, by drawing a triangle. So if you see, this is actually an equilateral triangle. So a center of equilateral triangle is at the center. So the center of positive charge for this structure is in the middle. Okay, now let's look at the negative one. Okay, so it turns out the negative is also forming an equilateral triangle, and the center of it will also be in the middle. So if you realize here, the positive and negative charge coincides. So when this happens, where the positive and negative charge coincides, that means the molecule is neutral. There is no charge. Okay, so keep this in mind because we're going to use the same knowledge in this next two diagram. Okay, so now if you see here, one diagram shows that it is the quartz crystal are expanding, the other diagram shows it is compressing. So what does this mean? Okay, so let's look at our transducer diagram. Okay, imagine now the ultrasound is being detected by the transducer. Actually, you got your baby inside here. This is the stomach. Then you put the gel. Okay, this is actually a very big gap, but yeah, it's actually a very small gap only actually, but I'm just showing it to you lah. Okay, so then when the transducer detects the ultrasound wave and eventually pass through the electrodes and to the quartz will actually start expanding and compressing like this. This repeated movement of expansion and compression will actually cause the quartz to vibrate. And when the quartz vibrate, it can actually generate something called electricity. And this electricity, this signal, will then be processed, and it can also be amplified and read by the ultrasound machine. That's how you see the baby image in the ultrasound machine. So what I'm talking about here is changing sound wave. In this case, we're talking about ultrasound to electrical energy, or just say electricity. Yeah, so this is detection of ultrasound. We're going to talk about generation of ultrasound in a while, but let's talk about the detection first. Okay, so now you get the idea. So now let's go in more detail on how it is going to produce electricity. Okay, so let's look at this first diagram where the quartz is expanded. So when the quartz is expanded, this quartz will now have distorted charges. So to say distorted charges, the more accurate way to say is they're going to have a dipole. Okay, how do I know there's a dipole? Okay, let's use the same color. Let's see the center of charge of the stretched quartz for positive charge. Okay, so if you realize, okay, wait, let me. Okay, so the center of charge of this triangle, and this triangle is not equilateral triangle, it's a bit stretched, and the center of this triangle would be somewhere at the base here. Yeah, so if you're wondering how do I know where's the center of the triangle here, so you can actually, there's a way to do this where you find the perpendicular bisector of each line. Then after that you connect all of it and you will find the center point. Yeah, if you're wondering how to draw that, I will link a video in the description below, then perhaps you can watch it and do it. But you don't have to be very accurate here. As long as you roughly know it's somewhere below, you are good to go. Yeah. Okay. So in that case, therefore, the positive charge now has been shifted upwards. Okay. Now let's see where our negative charge is. So we draw a triangle for negative charge, and you realize it will be a similar triangle, just that it's upside down, and therefore this triangle is the same triangle as the positive charge triangle. Hence, your center of this triangle will also be in the somewhere at the base there below. So if you realize, we have a, okay, you can't see the yellow color. Let me change color. Yeah, hope you can see now. No, okay, never mind. Let me pick. I think yellow. Oh yeah, yellow will do. Okay, yeah. So positive charge is on top and negative charge is at the bottom. So this has created something called dipole in the quartz. So this means the upper part of the quartz is positive. That is why positive charges are drawn on top. And since the below part of the quartz is negative, negative charges are drawn at the bottom. Okay. Now, what do we do next? Now this is where we're going to try to generate electricity. Remember I said there's electrodes at the side here? So this is where electrodes are going to come in. Okay. So I'm going to draw electrodes in grey color. This is one side of electrodes. Okay, I should draw below a bit. Okay. Just so you know, this two is not electrodes, okay? That is just to show that the quartz are stretching. Those are not electrodes, so please don't get confused. The one I draw are highlighted in grey up and below. These are electrodes, okay? So now what happens is, this part is negative. So ideally what will happen in the electrodes? Negative charges will start to repel. Negative charges from the electrodes, which is the electrons, will start to repel. Because negative, same charges will repel. So when electrons repel, okay, electrons are going to go here, through the wire. So the electrons will repel. So when the electrons repel, what do you think will happen to these electrodes? it will become more positive because the electrons are coming out. So this part of the electrode will become more positive. And since the electrons are going here, this part will become more negative. So if you realize, one part of the electrode has a very high potential, which is the positive side, and the other part, which is the negative side, has a low potential. So when you have one positive plate, one negative plate, one high potential, one low potential, what do you get? You get an electric field. That's right. An electric field is always from positive to negative. So your electric field is in this direction. So if you're wondering, wait, what causes the electron to move? I mean, not what causes. How can the electron move? What is the force that causes the electron to repel from this plate going to this plate? What would that be? So that would be electric force. And the electric force would be in this direction. It will be in the opposite direction. So how do I know the direction of electric force? Okay, let me take a color. So the way for you to know the direction of force in a field is when you put the charge in the field to see which is the direction of the force. So since your field is going in this direction, right? So let's say I put a negative charge here. Do you think it's going to attract here or it's going to repel there? It's going to repel. So force is downwards. That is why I say electric force is downwards. Same thing here. Electron, you put an electron here. This is a positive plate. Okay, you look at the plate. You look at the plate. Don't look at the charge here. You look at the plate now. Negative charge here. The plate is positive. So it's going to attract. So that is why the electric force is in this direction. So to put it simply, easiest way to understand this is, we know that the electron is repelling. And you know the electron is going to repel from here. So the electric force is in this direction. And the electron is coming in here. So electric force is in this direction. So if you're going to ask me that, is this really necessary to know for piezoelectric effect? No. I'm just explaining to you in case you're wondering why. Because I had the exact question, thinking how does this electricity is actually generated. The only thing that you need to know is, after the what we call the quartz has a dipole, it will create a positive charge on top and a negative charge below. And this dipole will cause the electrodes to have different potential. One is positive, one is negative. And when you have a different potential, ideally you have a potential difference. And there you go, you have your electricity. That is all you need to know. The one I explained to you about how electron moves, the forces, you don't really need to know. It's just if you are curious about it. Yeah. So the exact same thing now, we are going to apply to compression. So if you're wondering, is there current? Yes, of course. If there's movement of electrons, of course there's current. Electron moving in this direction, hence current is moving in this direction. Yeah. So there you go, you got electricity. Okay. Now let's look at the compression. Same thing, same concept. Now everything is just going to reverse a bit. So let's look at our center of charge first. For the negative, this is a very tall triangle. So the tall triangle, your center would be somewhere above here. I mean, it makes sense. Most of your tall fans are less stable, right? Yeah. So that is why why they are less stable, because their center is a bit above. Now same goes to the positive charge. It's just that same tall triangle, it's just that it's opposite. It's upside down triangle. And this here will be positive. So since the below part of the quartz is positive, here is positive, above will be negative. Okay, nice. Now this potential difference will give you electricity, because there's potential. Electrode up, electrode down. So this part of the electrode will be negative. Here electrons will repel, right? So why electrons repel? Because it is negative here. So electron repel, this electrode becomes more positive. And when you connect here, you're going to get a potential difference. Why there's a potential difference? Because you have one part is a higher potential, one part is a lower potential. You got a potential difference, there you go. You're going to have an electricity. So what happens is, inside the transducer, when the ultrasound enters the transducer, this quartz is going to expand, compress repeatedly. So this process actually happens really fast. So then the quartz will start vibrating. So this will actually create electricity. To be more specific, it will actually create something called alternating potential difference. Yeah, because at first, because what is alternating potential difference? Okay, imagine I connect. Okay, imagine here's the quartz, okay? Okay, this is your quartz. I think this is your electrodes. And this is the alternating potential difference. Okay, so at first, if let's say your voltage here is positive, here negative, that means this is your electrode here is positive, here will be negative. So when your electrode is positive, here is negative, you're going to compress, right? But if it's the other way around, now because it's alternating, right? So now it's going to go to the other cycle. Now here is negative, here is positive. What do you think will happen? It will expand, because based on this what we have talked about just now, when the electrode above is negative, down is positive, it's going to expand. Yep. So that is how electricity is generated, and that is how ultrasound is detected. Okay, get the idea? Right. So if you're wondering, is it always negative on top? Is it always positive bottom? No, it is not always like that. It depends on your structure. Like I say, if your structure is like this, yeah, this is it. If silicon is on top, it will be a little bit different, but the concept stays the same. Okay. So we talk about detection of ultrasound already. Okay, now let's talk about the generation of ultrasound, which is what the question wants. Okay. So generation of ultrasound is the opposite. Is when you apply an alternating PD to the structure itself for it to generate ultrasound. The detection of ultrasound, what happens is, you have your ultrasound, from the vibration of the quartz, you generate electricity. But in this case, when you want to generate ultrasound, you apply alternating voltage. Then this alternating voltage will cause the quartz to vibrate now. Compress, expand, and then you're going to give ultrasound. It's the opposite. Okay, let's roughly look at the diagram. Same concept, it's just opposite. So we have two electrodes here as usual. Two electrodes here. So, and we have an alternating PD. So let's say here is positive, here is negative. This part here is positive. This is the same thing I was trying to explain here. Yeah, positive. Then this part here is negative. So what happens if this is the case? You're gonna compress. Opposite side, you're gonna have positive here instead. What happens now? You're going to expand. So this process happens repeatedly. Eventually, you're going to generate ultrasound. So to simplify this, if you apply alternating voltage to the quartz structure, you're going to get an ultrasound. If you detect ultrasound, you're going to get an alternating voltage. It's the same concept, it's just opposite. Yeah. So we have talked about both generation of ultrasound and detection of ultrasound. So yeah, that's about it. So the main thing you need to know is the compression and expansion of this quartz is going to cause the quartz to vibrate. Then when the quartz vibrate, it's going to generate electricity. Wouldn't say electricity, more accurately is alternating PD, because you compress, stretch, compress, stretch, compress, stretch, so you're going to generate alternating PD. That is detection of ultrasound. You want to generate ultrasound, you put an alternating PD in the structure itself. You connect the structure to an alternating PD itself so that the quartz will now vibrate by compressing and expanding, and it will generate an ultrasound. Yep. So now let's answer the question. Let's go back to the question. Okay. So what the question asks, the crystal is made from piezoelectric material. Okay. Explain how the crystal is made to vibrate. So now they're asking about generation of ultrasound wave. How do I know it's generation? Read the question properly, okay? Crystal generates ultrasound wave. They already say generate, so that means they're asking you how to generate ultrasound wave. So your first answer will be, if you want to generate, you apply the PD itself. And make sure you write alternating PD across the crystal. Okay. Then, applying this PD causes the crystal to, you can say vibrate or distort, either one, doesn't matter. Yeah. Usually people say distort because you are distorting. At first you stretch, then you compress, you stretch, compress, right? So you say distort, but some might say vibrate also, like, mark scheme, right? Seriously. Yeah, but as long as you get the idea, it's best to check with your teacher lah. Vibrate or distort is the best. Because some mark scheme write vibrate, some write distort. So, yeah. Okay, so that's about it for Roman 1. Now let's look at Roman 2. So actually, this chapter, right, is actually from, this particular part is from medical physics chapter from A-level. It's full of theory. It's a very theory heavy chapter. The only part you're going to get calculation is when doing something like this, when using specific acoustic impedance, finding intensity, and perhaps momentum for gamma ray photons. The rest is all theory. This is a theory question, by the way. Yeah, so this is the most theory part lah. Okay, wait, oops, all the way down already. Roman 2. A parallel beam of ultrasound wave is incident on a muscle-bone boundary. Data for muscle and bone are given in table 4.1. Calculate the percentage of the intensity of the ultrasound beam that is transmitted at this boundary. Okay. A word that you should highlight here is transmitted. Okay, because the formula that you learn is not transmission, it is reflection, right? If you remember, which is I over reflection over I naught is the initial intensity, or you can just put it as I lah, no problem, doesn't matter. So the formula is Z2 minus Z1. Okay, you know what? Let me write it at the side. Just put as I, okay, which is the initial intensity. Incident intensity lah, we call it. Z2 minus Z1 square over Z2 plus Z1 square. This is reflected. So for you to find transmitted, what should you do? Just take 1 minus the answer. Okay, so if you're wondering why 1 minus, right? Okay, let me show you a simple math ratio. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so now this, the whole thing, of course, it's the intensity. Now, let's say I say 2 part is only reflected. So 2 to the power of 6, 2/6 is only reflected. So how much is the transmitted? It is the remaining one, which is 4/6. So if let's say this was a very complicated number, what you will do, you just take I minus IR, which is 1, the whole thing is 1, right? Minus 2/6. You'll get the remaining as transmitted. Right, same exact thing here. First you find your reflection, then you find your transmission. Okay, alright. So let's calculate. Also be aware they did not give you specific acoustic impedance. You have to calculate. And we know Z has a value equals to PC. You take your density multiplied by your speed of sound. Okay, let's calculate it. You're gonna get a very big value. I can assure you that. Yeah, wait, 1, 2, 3, 4, 5, 6. Okay, 6. 1.76 times 10 to the power of 6. The other one would be 7.79 times 10 to the power of 6. Okay, so let's calculate. And doing this calculation, do not forget to square. Also set, I'm going to set this as 1, I'm going to set this as 2. So this is my Z1, this is my Z2. So that you don't get confused. 7.79 times 10 to the power of 6 minus 1.76 times 10 to the power of 6 square times 10 to the power of 6 square, and you will get, calculate 0.40. So at this point of the answer, you can times 100% straight if you want, or if you don't want to also it's okay. So I'm not going to do it first, because I'm going to minus first, then I'm going to times. So like I said, this is intensity reflected. So intensity transmitted will be 1 minus 0.40, which will give you 0.60. And remember, times 100%. You're going to get 60%. If here you times by 100%, you're going to get 40%. Right? You don't, after that, go and 1 minus 40%, okay? You don't do that. It's 100% minus 40% already. Okay? So yeah, but I'm going to just leave it that way and times 100% at the end. And that is your final answer. So one thing to be aware here is, it's transmitted. It's a very normal thing. People just straight away use this. Oh, then there you go. So be careful for this part. Okay. So that's about it for today's video. I hope you gain a deeper understanding on how PZE effect in quartz works. I've explained about detection and generation of ultrasound, both, because they can ask about detection as well. It's just the opposite way. If you can understand detection, you definitely can understand generation. It's just the opposite. So keyword, expansion and compression of for detection. Okay, let's talk about the keyword. Revise back. If it's you want a detection, what you do is the quartz is going to expand or compress, which is going to cause the quartz to distort. Then the distortion of this quartz is going to give an alternating PD. But if you want to generate ultrasound, what you do? You apply the PD, then this will cause the quartz to distort and ultrasound waves is produced. So I just put generate ultrasound, detect ultrasound. Yeah. So remember to read the questions properly, whether they want generate or what we call detection. Oh wait, okay, I think I realized why the answer wrote distort. Because the question asks how is the crystal made to vibrate. So the distortion actually caused the crystal to vibrate like in the, yeah. So okay, yeah, makes sense. The answer was distort lah. Yep. Okay. So that's about it. Bye bye, and I'll see you in the next one. Take care and make sure to stay hydrated, okay?